So we're all infrastructure folks, and all of us were a party, I expect, to Apocalypse a couple weeks ago. And then for a lot of you, this is going to be sort of old hat. I'm talking about monitoring, why it's important, what do we measure. What's different and what you may not have seen before is this project I've been working on to make monitoring this sort of problem a little bit easier. So I work at Boundary, and like all of you, we run distributed systems. You might know me on Twitter as Afer. Basically, my job at Boundary and at Show You before that was to be the guy who did back-end streaming operations, database, all the distributed systems hats. And the reason that we use distributed systems is because they give us redundancy and fault tolerance, right? If you've got two machines and your probability of failure is 5% over some given interval, if you've got both of them, probability of simultaneous failure is 1 minus n squared. And so you can reduce that probability the more machines you add. The cost we pay for all of this is horrifying complexity, right? Clocks suck, and synchronization is hard, and state is hard. And all of this gives us failures. Failures that need to be instrumented. So my goal as an ops guy is to build the kind of infrastructure monitoring that I actually want to use for my own applications. The sort of stuff that I ask, and I expect you to too, is what's up right now. Every morning I check a dashboard. When I go to sleep, I check a dashboard. It's on my phone. It's on my desktop. And it sort of lets you explore the infrastructure to discover things you might not have expected. And it also tells you immediately what's wrong. But even more immediately than that, when you're not looking at the dashboard, it should be telling people via PagerDuty and via emails that stuff is breaking. At the same time, it needs to be a little bit intelligent, right? You can't have it send you emails for all of your failures, or you get complaints and ignore them. It's good to identify bottlenecks, right? You can ask, do we have enough CPU to support this application? What is our cost of goods? Like, how many theoretical users at this bandwidth can we support? And when you're fixing stuff and you push out a deploy, you want to know instantly, okay, has this broken something? And did my patch to fix it actually solve the problem? And the shorter that time is, the better. If you have to sit there and wait for 5 minutes for your Nagios poller or whatever to hit your app and figure out that it's broken, you're going to be sitting there for 5 minutes wondering, like, okay, did it work? Did this fix it? So I'm a big fan of low latency. You've probably used a bunch of these tools. I've been at this for a while, and so I started out with Nagios and Cacti. SNMP, right? Sort of that horrifying Byzantine abyss that it is. You've used Cacti, which is oriented towards graphs. Librato is a sort of modern Cacti in some ways, right? Provides you really awesome graphs, fixes a lot of the problems with Cacti, but it gives you the walls of charts that you need to really understand time series information in a quantitative way. The other aspect is not just numerics, but states. Things like, is the service up? Is it broken? That's what Nagios used to do. And now people like AppDynamics and New Relic look a little deeper at failure handling. There's a lot of infrastructure tools that are VM specific as well. So you might look at a specific JVM using JMX or CodeHail metrics or Netflix metrics. You could use Folsom to inspect Erlang. There's a couple Ruby libraries, metrics with a K. So all of these are good, and they're complementary pieces that I'm sure you guys use to figure out what's going on. The problem that isn't well addressed, I feel, is centralized state. For the really important stuff that's happening in your distributed system, you want a single place to view all of it. Not in depth, but just sort of an overview, so I can identify quickly what the problems are, and then use your in-depth tools to inspect deeper. The kind of lessons that I've drawn from these tools is that pollers suck. If you've ever waited for a Cacti poller, you know that it can take 5, 10, 20 minutes to poll a small network. So we use push events. You set up a server, and you listen for protocol buffers, and you just spew UDP or TCP packets at this thing, and it accepts them. That also lowers your latency, right? You don't have to wait as long because you're not waiting on an entire threaded poller to go and chug through a bunch of stuff. And it also means that you can have variable polling intervals. So instead of having to configure a poller to do lots of variable intervals for short and long stuff, each specific client decides on its own alerting interval. I prefer application level monitoring. I like writing code. And to solve the problem of operating system metrics, you write plugins just like Nagios. And finally, integration is important. I didn't want to build the end-all be-all tool because it would take forever. So I tried to provide simple handlers to glue systems together. Stuff that we measure, we if you pretend that you're an event happening in some distributed system, you might say like, hey, Zookeeper exploded, or hey, React's latency is way high, or SQL queries are timing out in this box. Those are state transitions. They tell you about the current state of the system over some interval of time. There's also incremental updates, stuff like I did 10 of this and now 10 more and 10 more. And there's also transient events, things like, hey, I caught an exception, but it's OK now. All of these I represent in Riemann as events. And the sort of fundamental constructs in Riemann are a client, which shoots these events over the wire, servers, which pick them up, streams, which react to the events and process them, kind of like a pipe system, and then an index, which gives you that stateful behavior on top of it. Events, as I speak about them, are keyed by a host and a service, which are arbitrary strings. You can namespace them if you like. Some sort of state, OK, warning, critical. Descriptions, which can be any amount of text you like. This is all UTF-8 safe, so you can throw JSON in there if you want more advanced state. Tagging, some sort of metric, floating point numbers, for example, Unix times, and times to live. When you want to send one of these, say with Ruby, you create a client and you shoot it a hash. All fields are optional, so if you want to treat this just as a numeric metric store like statsd, all you got to do is provide it a service and a metric. If you want to treat it just like a state store, all you got to do is provide states. Streams themselves, this is the interesting thing. Streams are functions. Functions in the JVM. So any Java, Scala, closure function that you can hand a map to is a valid operator in this sort of grammar of streams. And what do I mean by this? Well, let's say you wanted to talk about React, and you wanted to say, every time I get a critical state from React, send an email. This is what it would look like. You'd say where, and the service begins with React, that's a regular expression, and the state is critical. Go ahead and send an email to Delacroix. You can think of this like a little funnel, right, that collects all the events. That's the server, events coming in over protocol buffers. It's being pumped to a little where filter that's got a sort of a grate in there that keeps all the bad events out and lets the good ones through, and then a little email sender that shoots them out. Getting a little more advanced, this is a problem because you don't want to receive an email about every bad event. You only want changes when it goes down and when it comes back up. So we'll split it. You'll take all the incoming events. You'll get one pipe for each host and service pair by saying by host and service. Then we detect state changes. The changed stream looks for state transitions and emits only the first element in the transition. So if you go down, 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 up, up, you only see an up event. Finally, we roll up emails. So you can say, hey, every 3,600 seconds, send me at most 5 emails, and it'll accrue events in a buffer to make sure that you don't get overwhelmed. So altogether, this is a tree of streams, right? This is an X expression if you know Lisp, which describes a flow of events through Riemann. And the output of this whole thing is that you get little roll-up events telling you, hey, Riak on host azimuth had a get 99 of OK and critical over this time period. And then here's a complete log of all the stuff that happened. You can do a lot more, though. Because these are just functions and where is a macro that accepts any predicates, you can say where host is von Braun, where description is a regular expression. You can do tags. You can say we're tagged mutant. Arbitrary functions, so writing an expression like where the metric times 1,000 is greater than 2.5. And that makes range queries easy because the range operators in closure apply to every argument. This one here, where less than 5 metric 10, says where the metric is between 5 and 10, pass on an event. And any function you can define, right, an arbitrary function made up, can be applied here. So Boolean predicates are fine. Transforming events. All of these are, of course, immutable. But when you say with metric 1, it creates a copy of the event with the new metric 1 and then passes it on to all of its children. So this is a way for you to transform events within some context. You can also assign defaults. Splitting streams. Already looked at this one. This by expression here is actually a macro. It creates a copy of every stream inside of it, one for each combination of host and service. So if you need to do operations that apply only to a service, but to each individual copy of the service, you can do that easily. Integration with Graphite. Create a new stream, call it Graphite. This def here, this is an expression that defines variable, and then you can reuse it later. So wherever the service is web request by each host, compute a rate over time of a 1-second interval, and send it to the graph. So this is an easy way to replicate statsd, basically. You can pump these suckers around, transform them, compute rates, do differentials, do integrals, and then spew them out to different outputs. We've already seen the email one. You can do more advanced predicates, like if you've got teams for each different component, you can filter it out. Everybody on the controller component, if it's got tag controller, it'll be sent to one person. If it's got tag view, it'll be sent to another set of people. Throttling also includes rollups. So you can not only accrue all the events into one batch over some interval, but you can also discard ones that come too quickly. So if you need to cut down memory because you're getting spewed with hundreds and hundreds of thousands of events per minute or whatever, you can drop everything that comes after a certain threshold and then cut that even more down using a rollup. We can compute rates, percentiles, differentials, integrals, both in time space and in event sequence space. Here's a way that you can express percentiles. So if your service is shooting out messages like, hey, my API request took 13 milliseconds, then this sucker will accrue all those counts over time, over 5 seconds, and then it'll order them and take the median, the 95th, and the 99th percentile, and then emit those to you. So this is a way that you can generate quick aggregations and sort of selections out of a stream. Moving averages, EWB made timeless, right? Just gives you some sort of smoothing of a bumpy number. Where you need to fill in events, there are interpolation models. So you can say, if you've got a service like Riak, which may be telling you every minute about its state, but you needed to fill in a graph on Graphite every second, then you can use interpolate to repeat the last event seen over that time, or fill in to provide a default where nothing appears. This is really helpful when it comes to rates. State transition detection, you've already seen. You can split things by host and service and then look for state transitions in a service. Or you can just say change state and it'll do it for you.
Are those functions built in?
So getting a little weirder, combinations of states. If you've got a bunch of hosts that each report a service value over time, so maybe Riak is telling you that its CPU usage is X on each host, and you wanted to figure out what is the maximum of all of those. Coalesce remembers the last value of the service on each host that it encounters, and then gives you the last known state as a block, and you can combine it with some sort of fold. So this says, with the service's CPU, go ahead and remember the last CPUs you saw from everybody, and then tell me what the maximum one is, and I'll index that. So this is a way that you can do things like, tell me whether or not I have quorum on a database. If every one of your nodes reports in, or if a certain threshold of nodes report that they're up, you know it's OK. If some of the nodes are down, you know it's failed. And because these are just functions, you can define your own. Right in the configuration file, no recompilation required, you can write a new function like Librato. Takes an event, and it uses a little HTTP library to shoot these events over to Librato metrics. And then you can use it where service www latency, Librato, done. I've built several of these suckers just as one-offs, and it's amazingly powerful to be able to write your own adapters for in-house systems or for new APIs and just use them concisely as a part of your existing infrastructure. The sort of philosophy behind this is that I want to give you lots and lots of primitives that you can plug together in really generic ways to solve the problems you have. And the reason for this is that operations in general has incredibly specific problems. You're always dealing with an interaction of your software with some off-the-shelf stuff that was not really designed to work together, and the failure modes are unexpected, and nobody else has thought about them, so you're going to end up writing code. I'm a big believer that configuration is code, that a weak configuration language is essentially a weak language to solve your problem in. And so I've tried to make the configuration as powerful as possible to give you that flexibility. The sort of end product of all of this dicking around in Lisp is you get a dashboard. You've probably seen something like this before. You're probably using it already. This is just a table, an overview of all the different states in the system. There's a query language where you can express predicates over states using wildcards and string equality and numeric equality and booleans, all the usual stuff. So you give predicates to that, and it builds a big dashboard and gives you graphs. In addition, when you look at these suckers closer, they're actually bar charts, so you can see immediately like what the relation is to the disks. So all the disks are green, they're state OK, but API1.tx is using more. The they'll colorize based on state. So if something is critical, it'll become red. They're just CSS classes, so you can add your own. And if you hover, it'll show you the details. So the Riemann CPU plugin gives you top, basically. And this updates every 1 to 5 seconds. So you can hover over this sucker in the browser and just watch, oh yeah, I see immediately that the CPU is 5 seconds ago, it was 49%, and that 400% of the CPU in that box is going to React. So being able to just tab over the sucker in the browser really shortens the time to figure out what's wrong. Emails, we've already seen these. This is an exception email. So all the stack traces in pretty much every application we have that are unhandled that we didn't explicitly account for, we send those to Riemann. And then it becomes an easy process to diagnose problems as they arise. When something fails, you can investigate the failure mode, write code that accounts properly for it, and then no longer have to worry about it. This keeps us honest, too, in some sense, about our technical debt, and that you can't allow things to explode arbitrarily. You really do need to go in there and address the problems as they occur. We generate graphs. This is graphite. So this is a request latency we generated at show_you based on Riemann's output from each one of our API nodes. And then we can generate walls of charts. So this is watching React. This is a built-in plugin that comes with Riemann for watching React statistics. Stuff I'm working on now, new things. The dashboard as it stands is clunky HTML. So it's getting replaced with this crazy JS interface. I decided to write a window manager, and so it's got resizable panes and shit. It's a big project. The end result is you're going to be able to choose lots of different types of views, like live time series, like logs, so you can like tail a log file basically in the browser. You can look at the current sort of bar charts and so forth, and you can express those with arbitrary search indexes, and they'll be saved back to the browser, all as JSON. So this will all be live. End-to-end latency is somewhere around 30 to 50 milliseconds from event being created in your code to showing up on your screen in the browser. So that's pretty good. And the throughput that I'm getting is somewhere between 1 to 5,000 events per second. So it's unreasonable to parse a lot in the browser. Basically, I'm going to have to do some WebSocket deferring. This is the prototype as it stands. I'm looking at a log structured view telling me everything that comes through Riemann. So something like this will be one of the views that will appear. How does it perform? Poorly. On hardware show_you, when I benchmarked version 001, we pushed 11,000 events per second through synchronous TCP. This is a graph of throughput, which you can't see. That's all the CPUs. Because this is Clojure, it is really good at concurrency and eating all of your CPUs, all the STM, all the time. So it will happily scale to many cores. Above that, you can scale to multiple hosts. So Riemann streams can forward transparently to different servers. So you can set up a server for each functional group you want to measure, and then aggregate from those servers to higher level ones and the higher level ones. So you have multiple levels, both in terms of sort of spatial and in temporal resolution to handle large systems. Since then, I left show_you and now work at Boundary, and so I can't actually show you comparative benchmarks for how fast it is now, because that hardware is no longer available. The TCP server, in particular, I optimized a fair bit. It's now running roughly 3 to 5 times as fast as it was before. This is a drop test, pushing events in, deserializing them, and dropping them on the floor. The timescales are different, incidentally. This test is completing in 42 seconds initially, and now completes in 16. So optimizing this problem is something I'm focusing on. Because the UDP transport doesn't need to do as much of the TCP buffering and reconstruction, it can be significantly faster, between 4 to 6 times maybe. But it really varies on the streams themselves. If you're doing a lot of heavy processing of events, doing a lot of transformations and a lot of aggregations, then you have to pay more CPU costs for that. So where I'm going next, lots of optimizations, next generation web UI, persistence, so storing these events in OpenTSDB, in Graphite, lots of databases. And then a distribution story, which will probably involve Zookeeper and OpenTSDB in some form. The downside is I don't want to make people have to stand up a Hadoop cluster in order to use the product. So goal is to have something simple and you can extend it to be bigger. Working on correlations. Some people have asked me for dependency support to be able to say A depends on B, now when A fails, don't alert me about B. And then do some more intelligent sort of time series analytics around prediction and say, hey, 3 things just failed in your infrastructure. It's 3 a.m. Here's what you need to orient yourself. You need to know that database server's down and all of the application tiers down. And these things happened at the same time, so they may be related. And because I saw this failure first, it may be causally inferable that this one's the cause. I would really appreciate your thoughts. even if you don't want to help me build this, I want to hear what you want out of it, so I can help work out the roadmap, basically. So with that in mind, questions? Yeah?
What does this like help you debug at Boundary Origin?
Everything. At Show You, we monitored basically every important operation that happened, submitted an event to Riemann. And we had, I don't know, maybe 30 discrete services, each of which would report their cluster health and their processing throughput. We report all exceptions. At Boundary, we use the CodaHail integration that's in the Java client to shoot all of our CodaHail metrics into Riemann on a much slower timescale, so every 60 seconds. And that's because there's so many of them. That's nice because instead of having to plug JMX into a specific VM and like watch it, we can have unified walls of charts. I guess I don't actually have this on this laptop, but we've got a view that'll show us, for example, all of our VM GC allocations over time, and we can correlate those and figure out when cluster events happen and when Zookeeper drops because of a VM event, that sort of thing. At Show You also did a lot of business metrics, so we could tell you how many hours of video are being watched every day, how many people are liking things, commenting on them, user engagement, signups, clicks in the interface. So when we introduced a new feature or we changed the way a button worked, we could immediately see the response. Like as soon as it deployed, you'd watch that curve of new user adoption show up. So, yeah.
So has anyone requested a REPL because they're too lazy to write their own function?
A read execute print loop for Riemann itself?
For example, have you used Reconoider?
No, I haven't.
So it supports like a Cisco iOS style command line. They'll actually go back and do that. And like I've looked at your stuff and it's brilliant, but I'm just too lazy to write closure.
That's fine. This is intentionally aimed at people who want that kind of power, and I made the decision early on not to make it as simple as a cacti, not to have a web interface for configuring it, because writing that kind of program requires understanding the program structure. There may be something in the future, but it's not likely to be early.
No, I wasn't asking you to make it. I was just curious if anyone else.
No, nobody's asked for that yet. The requests are primarily for integration.
Well, I'm really lazy. So.
That's cool. I can tell you that standing one of these suckers up, like I've put a lot of work into documentation. There's a full site. It's got a quick run guide. You download a tarball. You run the binary that's included. There's a Debian package. So all that stuff should be pretty quick. As far as getting acquainted with closure in the streams, that's a longer process, and I've written guides for that as well. To answer your question in depth, the nice thing about doing this in Lisp directly as opposed to using another language is that because there are no functional objects representing because there are no like Java objects with metadata and a tree topology involved, you don't have to do all of the lookups for vars and dereferencing every time you go through a stream. So an event, when it sees a stream, it just sees a function, and the function has functions inside of it, more functions, more functions. The whole thing can be hit by the JIT in one pass. So it's really easy to optimize because all of this is just functional invocation. You don't have to do a bunch of traversal and thread safety around it. Referential transparency helps a lot in that. The other aspect is that I can do macros. So things like by can be implemented because they can capture the code form that you give it, and then they can use that to instantiate new copies of new streams on the inside. So that gives you a lot of power to reorganize and restructure your streams in ways that are intuitive to write.
Performance-wise, is there any overhead?
Yeah, I mean, it's closure, right? So expect probably the best it's going to do is about half as fast as the JVM for comparable expressions. My goal is fast enough. Officially aiming at 100,000 events per second, probably somewhere around 20,000 right now. But it depends a lot on your load. Like the 10,000 or the 11,000 number that I quoted earlier from Show You, that's a full production config, which has lots and lots of transformations for things like Riak and our internal apps. Something which is doing a simpler sort of aggregation, like just bringing together, coalescing, and forwarding onto Graphite, that can be much faster.
I think with that language, the one potential downside might be you need to have some really dedicated folks to understand the language. And
Yeah, yeah. Right, like this is not a faint of heart project. On the other hand, if you are infuriated by spending hours and hours configuring your existing software to do the job, maybe it's time for something more powerful. And that's kind of the threshold I reached eventually. Was like I can't spend any more time like fighting to get Chef to configure Nagios. I'm just going to write a program that does it the first time. And extensibility, right? Like being able to take any jar and suck it into Riemann and say like, okay, if I wanted to use Esper, sure, require the jar, transform the sucker into an Esper event, and then process it from there on. Like it's possible to do that entirely in the config as it stands.
right.
Cool.
So thanks.
That's good.